Alright, so in this video we're going to continue our discussion on angles. Recall that we have our special right triangles. We have our 30, 60, 90 triangle and our 45, 45, 90 triangle. Of course, these are described by their interior angles. But when we're looking at triangles like this, we have to realize that the edge ratios are pretty set. In other words, the side lengths of each one of these triangles are strongly connected. For some real number x, I can label the sides of the 30, 60, 90 triangle as follows. And these sides are always going to be proportionally related in this way. A similar labeling exists for the 45, 45, 90 triangle. So for either of these, once I pick a value for x, you essentially have the sides of these triangles, and again, we have these locked in ratios. What I can also do is describe each one of these angles here in radians. I have 60 for pi over 3, I have 30 for pi over 6, and 45 for pi over 4. These three angles are pretty important when we start studying the unit circle in one of the following sections. In a future video when we construct the unit circle, you're going to see this kind of picture and these angles pretty often, because they essentially serve as our building block for constructing the unit circle and for helping us evaluate trigonometric functions. In this slide we're going to talk about multiple rotations. Suppose that I look at an angle theta 1 with the following initial side and terminal side. And this is just going to be some positive angle theta 1. But now imagine that I have an angle theta 2 which experiences a full turn in the positive direction and has the same terminal side as theta 1. Suppose also that theta 1 corresponds to the angle 3 pi over 4 in radians. So since theta 1 and theta 2 have the same terminal side, can we say that they're the same angle or not? It turns out they are not. Theta 2 is not equal to 3 pi over 4 because it does have that extra full turn. In fact, theta 2 can be described as 3 pi over 4 plus 2 pi. Remember, 2 pi represents a full turn on the unit circle with respect to radians. And this is going to give me that theta 2 has a value of 11 pi over 4. And the terminology we use to describe theta 1 and theta 2 is coterminal. In other words, we say they are coterminal angles. Even though theta 2 has a value of 11 pi over 4, which lands at the same location as the angle 3 pi over 4, it depends on the context, really, on what value we really care about here. We're going to refer to 11 pi over 4, the original value, as the principal angle, whereas 3 pi over 4 is going to be called the reduced angle. Now, whether I need a principal or reduced angle really just depends on the context of the problem. The value 11 pi over 4 has embedded into it the number of times that I've gone completely around the unit circle. And that's the benefit of a principal angle. But the reduced angle doesn't care about how many turns I took, it just cares about where I landed. So to summarize this, the principal angle refers to the entire angle that has embedded into it all of its full turns. Whereas a reduced angle is going to be the non-negative corresponding coterminal angle that exists between 0 and 2 pi, or between 0 degrees and 360 degrees. So this slide is going to talk about how to take a principal angle and find its corresponding coterminal angle that is in reduced form. We call this modding out by 2 pi or modding out by 360 degrees. By modding out, we're essentially erasing the number of full turns in one direction or another so that I can find the corresponding coterminal angle that's between 0 and 2 pi radians. This chart is going to be sort of like a cheat sheet for us. The idea is as follows. If I have a positive angle in radians, I'm going to subtract 2 pi. In other words, I'm going to subtract a full turn. If it's negative, you add a full turn. And the idea is you keep adding or subtracting a full turn until your angle is between the correct interval. In other words, it's between 0 and 2 pi, or the number is between 0 and 360. So as an example, consider the angle negative 450 degrees. We want to find the corresponding coterminal angle between 0 and 360 degrees. Since this angle is measured in degrees and it's negative, I'm going to add the number 360 to it. When I do that, I'm going to get minus 450 plus 360 is equal to negative 90. Since the angle that I landed at is still negative, in other words not between 0 and 360, I need to rinse and repeat my process and add the angle 360 again. When I do that, I get the angle positive 270. So this is the reduced angle of negative 450 degrees. This means that 270 and negative 450 degrees are coterminal. That means if I draw them on the unit circle, they're going to have the same terminal side. So again, the reduced angle of 270 doesn't record what direction I went or how many times I went around the unit circle. It just cares where the terminal side is between 0 and 360. But negative 450 does have a little bit more information embedded into it, and depending on the problem, that could be useful. Next, look at the angle negative 23 pi over 6. I have a negative angle expressed in radians, so our rule says to add 2 pi. Again, since we're in radians, the addition of a full circle is the addition of the value 2 pi, not 360. But I need to find a common denominator. I can rewrite 2 pi as 12 pi over 6, and adding these fractions together gives me negative 11 pi over 6. This value is still negative, in other words, it's not between 0 and 2 pi, so I need to rinse and repeat my process. I'm going to add 2 pi again, or I'm going to add 12 pi divided by 6 again to get the angle of pi divided by 6, which is one of our special angles, so I know that this positive value is between 0 and 2 pi. Now look at positive 9 pi over 4 radians. This is negative, so I'm going to subtract 2 pi. By finding our common denominator, this means taking 9 pi over 4 and subtracting 8 pi over 4, which will give me pi over 4. Again, I have a special angle, so I know that this angle is between 0 and 2 pi. And now we have a picture of our coterminal angles. The biggest takeaway from this slide is to know how to take a principal angle and turn it into a reduced angle. We're also going to see a lot more special angles, like pi over 6, pi over 4, and pi over 3, as we get more familiar with the unit circle. In the context of applied problems, we have concepts like arc length, sector area, and speed. Recall that if I have a circle with a known radius r, I can compute its circumference, which is c equals to 2 pi r, and its area, which is pi r squared. Now suppose that I have some angle theta inscribed into the circle with a terminal side. Next, I'm going to highlight that portion of the circle which is being captured by that arc created by theta. The length of s is something known as the arc subtended by theta. And the length of this line s, or rather this curve s, can be given by the formula s is equal to r times theta. This is known as arc length. Now that wedge that's carved out, which we refer to as a sector with the central angle theta, has an area given by the formula a equals to r squared theta divided by 2. Again, this is called sector area. As you can see, both of these formulas completely depend on what my angle theta is. So if I had theta being a right angle or something bigger or smaller, I would get larger or smaller sector areas or arc lengths respectively. Alongside this, we have the concepts of speed, and I said that plural on purpose. First, recall that speed is defined as distance times time. If I have an angle theta inscribed in a circle with a terminal side, I care about two things: the linear speed of the terminal side and the angular speed of theta. To visualize this, think about a clock hand. Imagine that I'm looking at a starting point and a stopping point, and I'm seeing how far that distance traveled and what angle was actually taken. So to think about linear speed addresses the question of how fast the end of the arrow was moving. And angular speed looks at how fast the angle is either increasing or decreasing. It's completely fair to ask whether or not these are actually different things that you're studying, because you're essentially studying two different speeds of the same object, namely the clock hand. So are these things actually different? It turns out the answer is yes. They are different, and the difference is non-trivial. I want you to think about two clocks, a small wristwatch and a giant clock like Big Ben, for instance. Now, assume that we're in a perfect world and that every second hand of every clock in existence ticks at the same speed, namely it goes a full turn every minute. So the second hand on my wristwatch should be moving just as fast as the big clock in England. And that makes sense only if I'm talking about the angular speed. The angular speed is how fast the second hand is actually ticking, because even though they should be moving at the same rate, the second hand for Big Ben is a lot longer than the second hand on my wristwatch. So if I'm tracking the speeds of the ends of the arrows, the end of the arrow of the short second hand is going a lot slower than the end of the arrow for Big Ben. And it doesn't matter that the clock hands are ticking at the same speeds. The Big Ben arrow is traveling a much greater distance in the same amount of time, so it must be going faster. So that's why we have this difference between angular speed and linear speed. Angular speed, again, is how fast the clock hand is ticking in a circle, and the linear speed is how fast the end of the arrow is actually going. Now we're going to talk about how to find the formulas for angular and linear speed. All these things are going to depend on the angle theta, the subtended arc length of s, and the time that we're actually taking. So the formula for linear speed is given as follows. We use the Greek letter nu to define the formula nu equals to s divided by t, which I can rewrite that as r times theta divided by t. Angular speed is measured by the Greek letter omega and is given by theta divided by t. Let's look at an example. Suppose that I have the following latitude and longitude distance for Columbia, South Carolina and Daytona Beach, Florida. And just FYI, the values here are tailored for the purposes of this example, making it a little bit easier. So even though these aren't exact Latin lots, we're just going to go with them for now to make the actual angle we have to compute a bit easier. Now suppose that I'm going to take a 12 hours drive from Columbia, South Carolina to Daytona Beach, Florida, and we have to find the angular and the linear speed. Now the globe that I've drawn here shows that I have an angle when I go from Columbia to Florida, and that angle can be represented by the Greek letter theta, like we've been doing quite a while. And to find theta, I'm just going to find the difference between latitudes because the longitudes between these cities are the same according to this example. So I'll find that the angle theta can be written as 34 minus 29.25 equals to 4.75. I'm going to convert this value into radians because typically formulas like this are expecting angles to be given in radians and not degrees. Doing this is going to give me 0.083 radians. Now to find the length, I just have to find the arc length when I go from Columbia to Florida. To do that, I'm going to compute s equals to r times theta. And the radius of the Earth would be given in the problem. For us, it's going to be 6,370 kilometers. Multiply that by the angle that we've got, and we're going to get a value of 528.1 kilometers. So that's about the distance that we're traveling from South Carolina to Florida. And we're also assuming a straight line distance here, but again, we're given some leniency here because of the problem for computational convenience. So to compute linear and angular speed, we need the arc length s, which we have, we need the angle theta, which we have, and we need the time t, which was given to us in the problem. This allows me to compute my values for nu and omega as follows. For our linear speed, we'll get a value of 44.01 kilometers per hour, and for our angular speed, we'll get a value of 0.007 radians per hour. Alright, well thank you so much for watching, and join us in section 7.2 when we talk about triangle trigonometry.